This recording is for Chapter 3, Section 5, Mathematical Modeling and Variation. If you guys would grab your notebooks and open up your textbook to Section 5, we'll get this started. All right, so if everybody's on page 289, we've been talking about different mathematical models. One of the main ones is a linear model. In class today, we were talking a little bit about scatter plots and how oftentimes in a scatter plot you have positive or negative correlation. In other words, the dots kind of line up. If you have that kind of a correlation, a line of best fit can be drawn through the center of the data, and an equation of that line can model the data. That helps us make predictions or figure out different data that doesn't appear in the graph and so on. The tricky part about that is if you have a lot of data, it's very time consuming. So we were also talking in class today about how there is a regression feature to your graphing calculator that can be used to graph that scatter plot and potentially come up with a line of best fit for you. All right, so on the next slide, I've attempted to come up with steps that will help you guys punch that in. Some of you are having trouble with the window, not being able to see your graph. If you still can't figure that out by playing around with it, we'll just kind of try to figure that out together when we have class, and we might need to bring in Mr. Torgerson or somebody to help us with that. So here's my page with my steps. Hopefully that will get you back in there and right where we were in class today and play around with that. So this one goes along with checkpoint number 2 that's in your book, and that's the data that we had loaded up together when we were in class. So see what you can do with that. If it doesn't make any sense, we'll come back together and figure it out in our next class period. All right, another linear model or another mathematical model is direct variation. This should sound familiar. You worked with it in algebra and in algebra 2. Direct variation is when y varies directly as x. These models have the form y equals kx because the y-intercept is always 0. There's not going to be that number at the end like in a y equals mx plus b. K is called our constant of variation. So y varies directly as x can also be worded y is being directly proportional to x. The equations or the models will come in the form of y is equal to kx for some non-zero constant k. Let's take a look at checkpoint number 3. This will give us some practice with this stuff. The simple interest on an investment is directly proportional to the amount of the investment. An investment of $2,500 will earn $187.50 after a year. Find the mathematical model that gives the interest I after 1 year in terms of the amount invested P. All right, so where this tells us that we have a directly proportional amount, we know that we're looking at a direct variation situation. So in this problem, if interest varies directly or is directly proportional to the amount of the investment, we could look at that as I is equal to some rate times our principal. Okay, the rate would act or be our K in this case because that's the part that could or would change. Okay, the principal, the amount invested, that's a set amount. Our interest is earned from that, and it's going to vary based on the rate that we're working with. All right, so take a look at that model using the numbers from our problem. Our interest we're looking to earn is $87.50. The principal was $2,500, and then the R we did not know. Okay, dividing both sides by 2,500, we're going to get 0.075 for R, and then we can write our linear model as I is equal to 0.075 P. Okay, can you see the y equals kx form up there? Direct variation can also occur when x is risen to a power. So y can vary directly to a power of x. The area of a circle is one situation that would be like this. We all know that the area of a circle is pi r squared. So area is always directly related to 3.14 times that power or second power of r. So here again it is in summation. Number 1 up there says y varies directly as the nth power of x, which can also be worded y is directly proportional to the nth power of x. And that model would look like y is equal to kx to the n. Checkpoint problem 4 works with this. It says the distance x an object falls varies directly as the square of the duration t of the fall. An object falls a distance of 144 feet in 3 seconds. How far will it fall in 6 seconds? All right, so when we're looking at this one, we have the distance it falls. They used x, but honestly I'm going to use d. Distance is equal to some constant times the square of time. All right, so let's play around with the numbers that they gave us here. The distance of our fall is 144. We don't know the constant of variation, and the time that we're talking about is 3 seconds. So solving this one out, 144 is equal to k times 9. Divide both sides by 9, and we're going to get 16. So if we're going to figure out how far it's going to fall in 6 seconds, use that constant of variation and set up a new problem. Distance we don't know for the new fall. Our constant of variation is 16. Our time is going to be 6, and we need to square that. So 16 times 36. And if you punch that in, 16 times 36 is 576. Direct variation is a case where when the x value increases, so does the y. All right, so as x goes up, y goes up. That's direct variation. We also have a model called inverse variation, and that means that as the x value increases, the y value is going to decrease. This model looks a little bit differently. For the inverse variation, our model is going to be y is equal to k over x. So instead of k times x, it's going to be k over x. Take a look at checkpoint number 5 with me. Again, with all these checkpoint problems that we do together with the video, there's one in the book that's completed for us as well, so don't forget to look through those. All right, checkpoint number 5. The company in example 5 has found that the demand for another of its products varies inversely as the price of the product. When the price is $275, the demand is $600. Approximate the demand when the price is $325. All right, so we've got an inverse variation here. So we're looking at our demand being inversely related to our price. So D is equal to K over P would be our model. So let's fill in the numbers that we know. If our demand was 600, it told us that the price would be 275. So if we work this equation out and solve for K, K ends up being equal to 1650. So let's use that information now to find the new approximation. What will the demand be if K is divided by the new price, 3.25? And if you punch that in your calculator, our demand would end up being 508 units. Sometimes a problem can have direct and indirect variation in it. Take a look at example 6 in your book. This is one example of when you have both a direct and an inverse variation going on. We're going to do the checkpoint problem at the bottom, which gives us another example. All right, in this problem, the resistance of a copper wire carrying an electrical current is directly proportional to its length and inversely proportional to its cross-sectional area. Given that number 28 copper wire, which has a diameter of 0.0216 inches, has a resistance of 66.17 ohms per thousand feet, what length of wire will produce a resistance of 33.5? All right, so there's a lot going on in this one. It's telling us that our area, or our resistance, is directly related to length, but inversely related to area. All right, so look at your model. Let's write that out. Resistance is, okay, if it's direct relation, directly varied, you'd have your constant of variation times length. Okay, it said that length was directly varied to our resistance, but it said inversely related to its area. Okay, remember inverse variation was the K over the amount. All right, so that's going to be our model. Now we have to find our stuff. First of all, our cross-sectional area, we need to figure that out. Now what they mean by a cross-section, we're working with wire here. So if you cut the wire and you look at it straight on, it's circular in shape. So the cross-section or the cut is going to be a circle. So we need the area of that circle. Now notice in our problem here that they give us the diameter of the wire. We know that to find the area of the circle, we need pi r squared. So that's the first thing that we need to take account of. Pi times, now the radius of that is going to be 0.0108, and we square it. That area, if you punch that in, ends up being 0.00037. Okay? Now the other thing that we should look at, so this one's A. We have R is resistance. So the resistance that they gave us in this first one is 66.17. So we've got that. Length, take another look at the length. It tells us that the length is 1,000 feet. The problem with that is it doesn't match our other label, which was in inches. So we're going to take that 1,000 feet and we have to make a match. So it's very easy, multiply it by 12, and now we have inches, and then that matches our unit of measurement that was on the wire. And our constant of variation, let's just keep with K. And we don't have that. So our first setup, our first resistance, 66.17. Length, 12,000. Area we found, 0.0037. If we punch that through to our calculator, we're going to end up with a K value of this. Now we can go and we can find that new resistance. So if we're looking for a resistance of 33.5, or new length I should say, we got the new resistance. 33.5, K we just found, 0.0000204. We don't have the new length, and our area of our wire isn't going to change. It's still the same wire, so fill that in. Now when you punch that in, we're going to get 6,075.9 inches for our length. Many people would probably convert that back to feet. So if you divide by 12, we'll go back into feet. I don't care which one you leave it in. Joint variation. Okay, sometimes it's possible that you'll have two things that are directly or proportionally related to another. Okay, so in joint variation, we need to consider that we might have z equal to both x times k and y times k. So two things vary directly with z. All right, so let's take a look at that a little bit closer. Simple interest is one thing that does. You have all worked with that formula before. Example number 7 in the book deals with a simple interest problem. We're going to look at a different situation with the checkpoint problem that's underneath it. So you guys go ahead and look through the book example number 7. I'm going to take you through checkpoint number 7. Checkpoint number 7 deals with kinetic energy of an object which varies jointly with the object's mass and the square of the object's velocity. Okay, so if we're looking for an energy that is directly varied, I'm going to have k times its mass and also its velocity squared. Okay, that would end up looking like this. Do you see how both the m and the v squared are multiplied by our constant of variation? It's like taking two separate problems and putting them into one. So working through this one, The energy that they give us in here is 6,400 joules. Fill that in. Constant of variation, we don't have it yet. The mass of our first situation is 50, and the velocity for that first situation was 16, let's see, meters per second. And we have to square our velocity. All right, so 6,400 equals k times 12,800. Divide both sides by 12,800 and you get a half. So with that constant of variation, let's figure out our new energy. Energy will be equal to constant of variation times the new mass times the new velocity squared. If you put all that together, we get 14,000 joules. All right, that's it for me. Your assignment, turn to page 296 in the book. As always, you need to do a lot of practice with these problems, and some of you have not been doing much. I have assigned 5 of them that I want turned in, numbers 14, 20, 44, 64, and 72. So make sure that you spend some time this weekend and get comfortable with this. It's the last section of our chapter, so our test is coming up soon.